stars, and then kind of hold the whole star thing. It's so exciting. We'll start stars on Monday. I know. I just think, is our sun a star? Yeah. Is it like a humongous star? Is it like a tiny star? It's like in between. It's like dead center in kind of how stars do their thing. So we'll kind of put that in perspective later when we talk about stars. So the second part talks about space weather. And hopefully you're going to kind of remember the video that we watched, kind of remember some of the dynamic things you saw. So what does dynamic mean to you guys? Moving. Dynamic is moving. What would be an antonym of dynamic? Static. To me, I'm liking static. Static. So the sun is dynamic, right? So it's got a personality. Okay. We actually call it kind of two moods. If the sun had two moods, we call it the quiet mood and the active mood. And I've got the video we watched kind of, well, I should say, actually I kind of got ahead of myself. These are things that we talked about Wednesday. This is Friday. These are things we talked about Wednesday. Did we talk about granules Wednesday? Okay. So what layer of the sun are granules found in, kind of? Photosphere. I kind of associate with the photosphere. Are they always are they like static, like a circle is a granules? Does it always look like that? It kind of moves. But are granules always present? Yeah. Supergranules, I don't know if I necessarily talked about that on Wednesday, but supergranules are kind of what they say. Supergranules are where the photosphere kind of lifts up, kind of has these big pockets of granules that are kind of a big hunk of deal. We talked a little bit about spicules, didn't we? Yeah. Are spicules always there? Yep. Solar wind's always there. So this is to say whatever mood the sun is in, whether it's active mood or a quiet mood, the sun always has these things. So these things in bold are transient. These things in bold that I have in the third bullet here are only associated with an active sun. These are with an active sun. So that's to say that if the sun is quiet, these things are not there. If the sun is active, these things may or may not be there. I'll go ahead and circle sunspots because they're so important. We kind of use that as a marker. We use sunspots as a marker to determine the sun's activity. Okay. So here in a minute, you're going to see, I think kind of like we might have seen on the video, you're going to see basically a plot, a figure, where along the y-axis is the number of sunspots and along the x-axis is time. So sunspots, plages, filaments, prominences, coronal holes, and coronal mass ejections. Coronal mass ejections is the granddaddy of them all. This is scary. What's scary next to CMEs you can. So anybody remember the number associated with the cycle? Like how many years is it? 11, exactly. You're going to see it in your notes here in a minute. It's an 11-year cycle. It kind of goes, we call it maximum when it's active. We're going to have most sunspots. Minimum suns, and it's minimum when it's quiet, minimum sunspots. Very cool. And we're going to see actually the last slide is going to, in this part, is going to talk about why the sun goes through the cycle. It has to do with the magnetic field. Does the Earth have a magnetic field? The Earth's magnetic field is nice and tame compared to the sun's magnetic field. Okay, but basically the Earth's magnetic field, remember, kind of goes from the north magnetic pole to the south magnetic pole. I don't think we talked about this much, but aren't you curious when you read in the news about this isn't the sun, it has to do with the Earth, this idea of the Earth's magnetic poles flipping? That's a real deal. That's not fake news. Okay, so they've flipped in the past. They'll probably flip again. When they flip, that won't be a very good thing. Actually, the movie 2012, I mean, like the science fiction movie, I think it had to do with the flipping of the magnetic poles and leaving Earth vulnerable during that time. Anyway, I digress. Okay, sun. Okay, so space weather talks about which mood is the sun in? Is the mood active? with lots of sunspots and all these other things go along with sunspots, or is the sun, did I say moon? Or is the sun quiet with few sunspots? Okay. So space weather, and on my slides I have, to reinforce what the video said, we care about space weather because we have, they're called assets. Isn't that a cool word? Assets. Assets could be people or equipment or other things, but we have assets in outer space that are vulnerable to when the sun is active, because with the activities, with the flares and the coronal mass ejections, that it's spewing charged particles. So anyway, this is kind of a series of sunspots. A lot of times sunspots come in what are called sunspot groups. So sunspot group. And we're going to look here in a minute, my favorite website, to look at solar activity, see what kind of sunspots we have going on. On Tuesday, or whenever this Tuesday or the following Tuesday, when we get the telescopes out and properly fit them with the solar filter on the front, I've got another cool telescope that all it does is look at what's called alpha hydrogen, the element hydrogen, alpha hydrogen emissions from the sun. So I'm going to grab that one first. What I started to say. But if that's the case, hopefully we'll see some sunspots. So this is a close-up of sunspots. And if I were to animate this, I think you might have seen it on the video the other day, that it definitely, just like the granules kind of change their shape, so sunspots change their shape. They are transient. They kind of come and go. So kind of speaking of transient, this has taken a series of photos of the sun. Doesn't say who took it, but Galileo, we talked about Galileo, who actually used his telescope to look at celestial objects. Did Galileo invent the telescope? No, Galileo did not invent the telescope, but he used it to actually see the moons, for instance, of, what planet did he see the moons of? Jupiter, yep. But Galileo could actually see features on the sun and moving, rotating. Now, I couldn't find it in my slides, and I'll go ahead and write it on this slide. I'll go ahead and say 4 weeks. 4 weeks, which is about the same time it takes the moon to complete one orbit about the Earth. And also remember that synchronous rotation, the moon takes about 28 days to complete one rotation on its axis too. The sun takes about 28 days to complete one spin on its axis. It has differential rotation, kind of like Jupiter though, and the video talked about this, where it's moving, do you guys remember where is it fastest? It's like Jupiter. Is it fastest near the equator or the poles? It's fastest near the poles, which kind of seems weird to me. It's fastest near the poles and slowest near the equator. But if you kind of look closely, you can see where kind of this sunspot group is kind of morphing. So for instance, here you see this is decaying. I kind of see that kind of getting smaller, that feature. Maybe this feature is getting larger. If you kind of try to, it's kind of hard to track, but. Okay. So that image looks different than this image. Now this image is taken, I like Soho, which I just think that is so funny. This is SDO though, SDO. It's a spacecraft that, I didn't double check. Is the spacecraft in orbit? I think it's in the same orbit as the Earth orbiting the sun, I think. Because otherwise, if it orbited the Earth, it couldn't always see the sun. You can double check that. So the SDO. And it takes some neat infrared pictures. This is infrared. One of the features of an active sun are these things called coronal holes. And honestly, you kind of need to know what you're looking for. I don't necessarily know what I'm looking for. Kind of these bright regions, I think, are the coronal holes. There are bright holes and dark holes. And as I understand it, the coronal holes in an active sun are kind of like conduits that go kind of, in a sense, through the sun and come out the other side. It's kind of weird. I mean, they're not like holes like you could fall through it. But, and you can't see them in the visible, you can't see it on the visible wavelength. So this is changing it up. And this is looking at just simply one very narrow region of light. and trying to kind of highlight, this would be your sunspots, okay? And you can kind of see these light regions that otherwise wouldn't come out. These are your phages. The bright regions are your phages. And I'll go ahead and up here, phages equals filaments. They are the same thing. They're again associated with an active sun. Filaments just simply means that actually you're seeing them, must be you're seeing them kind of raise off the surface. Can you read my handwriting up there? Filaments. Filaments. Active sun, active sun, active sun. It's not always like this. So this is showing you a prominence, and I get my solar features mixed up, but it definitely looks active, a prominence. Now, to me, and we're going to talk a little bit, what was the granddaddy of them all, I said?
Coronal mass ejection.
Coronal mass ejection. To me, a difference between a prominence and a coronal mass ejection, which we're going to see here in a minute, is a prominence doesn't look like the stuff is still kind of, gravity is keeping that stuff associated with the sun. Coronal mass ejection is the material is literally ejected so fast with so much energy that it escapes the gravity of the sun. So prominences still stay as part of the sun. This actually, if you read the caption, and I don't know which way, I'll just go ahead and say like this, 1, 2, 3, 4. Those 4 quarters are actually taken during different times. Let me see what they call these. Yeah, they're calling these prominences as well. In ultraviolet region of the electromagnetic spectrum. So active sun, looks active. This is
4 looks like a upside down ribbon.
It does look like an upside down ribbon. So if I were to ask you, temperature wise, what do we got going on? What's the outermost layer of the sun's atmosphere?
Corona.
It is called the corona. Temperature wise, how would you compare that to the photosphere?
Hot.
Very hot, yeah. And I think the video we saw kind of talked about spicules as maybe kind of transferring energy, so it kind of builds up. But to me, I can almost see this kind of transferring energy up to the sun's atmosphere. Coronal hole. Let's see, bright side of the sun, images. Solar flare. To me, this kind of looks like a coronal hole, but this is a solar flare, and I'm like, all right, solar flare versus a prominence. I suppose it doesn't have the loopy part to it, does it? Solar flare. Solar flares are probably more common than prominences. Solar flares, I know and I've read, are oftentimes associated with sunspots or sunspot groups. You'll get these solar flares. Solar flare is more of a smaller burp.
That one that's up on the top right there, that looks like a solar flare. Not right there where you're, yeah. That looks like a solar flare, but if you come down a little bit, no, go down on the outside there.
Oh, here?
Yeah, it looks like it's looks like a rainbow type thing. Now, is that a prominent?
It could be. It really could be. You're saying kind of this right here?
Yeah.
Yeah. I don't know.
Just to make sure that I'm getting it.
Yeah, and it really could be. So I don't know. To me, and I don't know, I might be trying to interpret too much into it, but do you remember the video we saw? And it kind of showed these, I'm pretty sure the video called it spicules, kind of the little, kind of like the little hair standing on end sort of thing. And I'm not sure if those would be spicules or not in this, and it kind of, we've talked about different energies of light, the different forms of electromagnetic radiation, and a scientist smarter than me would know when you're looking at this wavelength, what features are you going to see? This wavelength, what features? So, all right, what do you think about this one? It's saying solar flare, but I'm kind of thinking materials ejected here. Maybe to be a CME, a coronal mass ejection, it needs to be more energetic than this. But can you see that stuff here? Now, the problem is, or the reality is, if the Earth is right up here, it's kind of a directional thing. If we're in the line of sight of an ejection of material from the sun, that's when we're in trouble. That's when space weather says, everybody batten down the hatches. And we have, I'm thinking about 8 minutes before the energy gets to us, and then a few days before the particles get to us. All right, so coronal mass ejection, I guess they do look bigger. That looks smaller, and they're associating with a flare. But this would be, you can kind of get a scale, sort of the scale sort of thing going on here. This would be a coronal mass ejection. And then this right here, so this is a photo, and I don't think that this is a photo. I think this is a figure. So what is that right there? That's Earth. That's us. That's Terra. What are the blue kind of cool looking things coming out of there?
Magnetic field?
Our magnetic field, exactly. That is our protection from stuff from the sun. Yep. And if you ever come across cool astronomy websites, send them my way. I know Barry sent me a few. He sent me one about the Northern Lights. And actually remember that Northern Lights are related to space weather in the fact that our magnetic field, our magnetosphere, magnetic field can only accommodate so much charged particles from the sun. And actually they're stored in a region called the Van Allen belt. It's kind of like a pair of donuts around the Earth. And so they're kind of like shock absorbers a little bit. And when those Van Allen belts get too full, then actually the charges leak through the holes. That gives us our noise. Yep. So what do these look like over here? Sunspots. I'm liking sunspots. I think this is showing you, well, it says through the evolution of time, a giant eruption on the sun. Sunspot group. We're changing the wavelength, we're looking at it, okay? And so this, to me, kind of corresponds there. I read the caption at my desk before lecture, but this actually doesn't, this kind of goes back to our CME, our coronal mass ejection of material out into what you're looking at, kind of that sort of, that is the sun's atmosphere. That's the corona that you guys told me was very hot. Okay, so how does this work? I think I read the caption, and that circle right here is the surface of the sun. Starts with the letter PH. What do we call the surface of the sun? The photosphere. Yep. So that would be the photosphere, and then this is your coronal mass ejection. And I was going to look it up. I think an angstrom and a picometer differ by a factor of 10, but these are just wavelengths. 171 angstroms, okay, getting longer wavelength as we go across. Oops, that's not a wavelength. But just looking at, again, trying to massage all the information we can from the sun. We see some terms we've been talking about in the previous unit, or the previous part and this part. Sunspot, photosphere. I'm really not sure. This says chromosphere. Remember, the chromosphere is between the photosphere and the corona. So I'm not, to me, I'm not liking that figure. But here's the corona, you can see during an eclipse. Okay, coronal holes, which we can't see with our naked eye.
I think that corona hole, if you went back to that slide that you had,
okay,
it looked like that black section down on the bottom was probably the corona hole.
Okay, corona holes can be bright or dark, so
okay.
Yep, that sounds right. Sounds right. And on the test, I'm not going to give you like, I'm not going to require that you look at the surface of the sun and identify what active feature it is. I just want to I want you to generally know what active features are. So, cool. So 11 years, very good. 11 years, but actually they can range from 7 to 15 years. The thing about those sunspots, and sunspots are what we track to gauge the mood of the sun. The thing about sunspots is they are cooler regions on the surface of the sun. So if we have a lot of sunspots, then actually we have a dampened amount of energy coming in our direction. Okay. The movie The Day After Tomorrow, which is kind of old now, but I like it. It's a classic. And one of the things, it's kind of a long story, but when the weather went wacky, the scientists got together and asked NASA, okay, is the sun doing anything strange? And the answer was no, so it's something else. But cool. And this actually kind of talks about why do we have the SOHO, I love that, or the SDO, and the stereo, they all have the nose, okay? Why do we care about looking at the sun? And those, by the way, were just on the United States missions primarily. So now I'm trying to think some of those missions might be international. But there are other nations that are doing the same thing of trying to get a fix on what the sun is doing or not doing. And it's to protect assets, but it's also to understand our star so we can understand other stars. Okay, this is the ISS. So what does that stands for? International Space Station. And what are these? Solar panels, yep. And so if you, for a given night, if you're doing some viewing, there's a website that you can look up. Go ahead and say what it is. It's called, I probably did this before, Heavens Above, all one word. Oh, no, it's not. It's Heavens dash above, and it's not an underscore, it's a dash.com. So that website, you can see when the ISS is going to be flaring, and all flare is that from your perspective, and it doesn't flare for everybody, but for your perspective, they've done the math, and the angle of these solar panels and where the sun is and where you are all match up, so you'll see it kind of light up, and then it will dim out again. But anyway, that's something that cares about space weather. These people care about space weather. These are astronauts in training. I think so. Well, maybe. But astronauts is becoming vogue again. People are like, how can you do that? Northern Lights. Okay, so hopefully we've kind of talked about how this is connected with space weather. Okay. I wonder if that's, oh, must be coming up. Where's my little, I have a website to take to my favorite website. So let's see, what's the difference between the year 1996 and 2006? How many years is that? 10. Okay, so all this is trying to show you is kind of the cycle of the sun. So what do we think, novices that we are, what do we think these are? It could be a few things, but I'm trying to circle those bright things. What do you think? I'm thinking coronal holes, sunspot groups, or something energetic, but I'm kind of liking coronal holes for them. And you can kind of see where there's not many here, so this would be the minimum, this would be the max. M-I-N-M-E-S. You can't read my writing, which I can sometimes not read my writing. So this is the year 1750, just the other day, and this is the year 2000, and of course we're just the other day, and we're 2017. And if you're like me, sometimes I just dream of what life would have been like back then. Sometimes I wish I lived back then. Okay. And it's amazing to think that people cared and that they actually wrote down for each month. Each dot represents a month. That's how that works. Right there. To jot down what sort of sunspots we had there. So along the y-axis is the number of sunspots, along the x-axis is time. I think that is so cool. So spaceweather.com, we're going to take a quick look. And that is my an awesome place if you're wanting to know what the solar activity is doing. For Tuesday's lab, I will visit this website for Tuesday's lab, and I will take a look here, and I will see what do we hope to see through our telescope. And the answer, if we were out there today, would be these guys, these little pinpoints, which are sunspots. Now for the it's my gold telescope. It's not my telescope, the school's telescope, that alpha hydrogen line telescope. That one we should be able to see flares on the limb of the. So anyway, there's that. There also, if we scroll on down there on the left, is a place to kind of see what you might expect for northern lights. Okay, so where it's green is where you can probably, hopefully, see some northern lights.
Why are we taking a field trip?
I don't know. Well, as I'm reading this, I mean, there's, I don't think this is real. I think this is sometimes black. Do you know what I'm saying? This is sometimes, or gray, this color. So, I don't know if there is a slim chance. What direction would you look to see our lights? North. Northern lights, yeah. North. Yep. Yeah. There was something that caught my eye, and I want to play it for you right quick. This one, if I can pause this. So if you have a test question that kind of asks, that asks why does the sunspots increase and then decrease, kind of an 11-year cycle. So from peak to peak is 11 years, from minimum to minimum is 11 years. And the answer is the sun's magnetic field. And I'm pretty sure that the video kind of touched on this too. What this figure shows you are these two little dark spots are just normal sunspots. And I think what the video kind of showed you is this is actually it's kind of like it's a magnetic field. You know how the Earth has a magnetic field that goes from pole to pole? Well, the sun has these little magnetic fields that go from sunspot to sunspot. And in fact, they trap, so this would be a sunspot, this would be a sunspot, the invisible magnetic field, and you can see the charged particles caught in this little loopy thing. All this little loopy thing connects to sunspots. Okay, that happens all the time on the surface of the sun.
So, what's the question? Why does the sun what?
Why does the sun have, the next slide's going to kind of show you, maybe on this one. Why does the sun cycle every 11 years for its activity? And what sort of rotation did I say that the sun, and this is part of it, what sort of rotation did I say that the sun has from the poles and the equator?
28 days.
Differential, 28 days for the whole thing to cycle around, but it's not the same, is it? So which one goes faster? The poles go faster, yep. And so because of the differential rotation and the magnetic field, it's kind of like playing Twister. It's like, let's just say you are here and put your hand here and put your foot here, okay? And then you put your other hand here and your other foot here, and then go ahead and start the differential rotation. So go ahead and start, this part's going a little slower, this part's going a little faster, okay? And so you get totally like whacked out, okay? So this is kind of showing you the differential rotation, okay? This is showing it going. It's faster at the, oh, you were right. I need to double check that. This says the sun, yeah, Hannah. The sun spins faster at the equator than near the poles. So,
Oh, they were talking about, I thought we were talking about Jupiter, Saturn, or whatever planet it is that like
yeah.
also has the dance.
Yeah, it does. So it's going faster at the equator and slower at the poles. You can kind of see that here, and I'm not doing it justice, but it's kind of like playing Twister, and then at the end of, let's see, to me, half, I think of it as kind of half. At the end of, half of 11 is 5.5. At the end of 5.5 years, it just kind of goes wacko, and it kind of breaks it, and it kind of resets. So then it goes back in the number of sunspots. So, okay, clear as mud. Well, that was the last slide, and just to plug that, I haven't done it for like ever. I haven't ever done it here, but they do have a blood drive today. So consider giving blood. But don't give blood if you haven't eaten yet. No. So this homework is due, and let me know if you have any questions, and that's it.